Yeah. Cool. Let's turn the mic off. There we go. What are we doing? We're doing limits today. Okay. Let me share the screen. My internet connection is unstable, it says. Well, makes sense. Everything else in my house is unstable as well. So why would the internet be any different? Okay. Okay, 1.1 is on limits. Okay, so limits. What's a limit? Okay, let's look at a theorem here. Theorem. If a function approaches the same value L from the right and from the left, then we say the limit of the function is L. Okay, so the limit of the function is L. Okay, so the technical way of writing that is if the limit as x approaches a from the right, the plus sign is from the right. Okay, think of positive x values. Okay, from the right, this plus sign from the right, as x approaches a from the right, or from above, excuse me. Okay, from the right or from above. Okay, of f of x. Okay, equals the limit as x approaches a from the left. Okay, from the left or below, from below. Okay, of f of x equals L, then we say the whole limit, and then we say the limit as x goes to a of f of x is equal to L. Okay. So now why would we need to do this? Okay, because sometimes we get functions that look like this. Okay. They have holes in them. Okay, this is a function that has a hole in it. It's called a discontinuity. Okay, and so we know that as we approach this thing from the left, from the right, it's going to approach a certain value. Okay. That value that it approaches is L. Okay, as we go from the left, it's going to approach the same value. Okay. And so we need to find the limit of this value. Okay. Real quick. What's real quick? Okay. Okay, so let's look at a limit where this behaves like this. Let's a function that behaves like this. Okay, so number one, find the limit as x approaches 1 of x squared minus 1 over x minus 1. Okay. Now, what is a bad value here? What's a value that we just can't have in our domain? What's the bad?
Positive 1.
1.
1.
0.
Anyone? Right. 1.
Yeah, 1. X cannot equal 1. Why? Because we can't get division by 0, right? We can't have division by 0, and so we can't let x equal 1. Okay. So x cannot equal 1 here, right? But that means that there's an empty value here. Now, why is there an empty value? Because this is going to graph a line except for x equals 1. And the way that I could see that, okay, is if I were to factor this, essentially these things are going to cancel out, okay, and this will be f of x equals x plus 1. That's just the function, the equation of a line, but we have to take into account that the original function couldn't have x equaling 1. That means that if x can't equal 1, then what can y not equal? If x can't equal 1, then what can f of x not equal? No, just plug it in.
1. Is it 2?
2. Okay, yeah, it can't equal 2, right? Okay. Let me mute everybody that's not muted. Getting a lot of background noise. Okay. So you can unmute yourself when you want to. But, okay, so if x can't equal 1, then f of x can't equal 2, right? Does that make sense? So if I plug in any other value for x, it's going to behave like this line, except at 1, which means that y can't be 2. What does that mean? It means I have a hole in my graph. It means that it looks like this. And it looks like x plus 1, y-intercept of 1, and a slope of 1, up 1 over 1. Okay. And so what's the supposed to be a 45-degree angle, but whatever. Okay, so there's my line, right? Except for the fact, what? That this guy doesn't exist here. Why does he not exist? Oh, he doesn't exist. Oops. Oh, now he really doesn't exist. Okay, why does this guy not exist here? Why is there a big hole in my graph? Because if x can't equal 1, then y can't equal 2, right? So we get holes in our graphs, and we have to basically say, well, what is this function really approaching? Okay, what is it approaching? As x approaches 1 from the right, it's approaching a value of 2. The function is approaching a value of 2. As what is approaching as x approaches 1 from the right? What is this approaching as x approaches 1 from the left? Well, isn't it still approaching this value of 2 here, right? This value of 2. So we're going to say that the limit as x approaches 1 of f of x is equal to 2. That's the limit. The limiting value here is 2. Okay, for f of x. Okay, we know what we're approaching with the x value. We're approaching, okay. Okay, for f of x equals 2. Okay, so that's the idea, is that there are sometimes these bad functions, and we kind of have to fill the holes on these bad functions. Okay, let's see what happens. Like why do we say that this is approaching 2? Well, basically, how close to 1 do you want to get? How close to 1 do you want to get? Well, maybe I want to get 0.9999999, right? Let's let x equal that. 0.9999999. Then what would f of x be equal to? Well, if we plug it into our original function, we could do 0.99999, 1, 2, 3, 4, 5, 6, right? 0.99999 squared minus 1 all over 0.99999 minus 1. Okay, so this is, right, this is f of x at 0.9999999. Let's go to a calculator on this one. Okay, so I'm going to do 0.99999. Let's do, that's really close to 1, right? 0.99999. Let's do 6 of those 9s. Let's square this guy. Boom, that's what that guy is squared. Let's subtract 1 from this. Okay, and I get negative point. Okay, negative 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 9, right? 9. How many nines here? 1, 2, 3. Oh, there's still 6. That's cool. 9, right? Okay, all over one. This minus 1. Well, that's going to be negative 0.00000. No, are there going to be 5 or 6 of these? I think there's only going to be 5. 1. Okay, let's see if we're right. So what's 0.99999? 9 divided by, or sorry, not divided by, minus 1. Okay, I'm going to get 1, 2, 3, 4, 5. Yeah, I was right. So 5 zeros. So I'm going to take this bad boy over here on top and divide him. And what am I going to get? I'm going to get 1.9999999. So that, which should make sense. 1.9999, it's 6 of them. That's nice. Okay, so 1.9999999 is really close to what number? Really close to what number? What number is that really close to?
Yeah.
Of x. Anybody know?
2.
2. Yeah, 2. Okay, So it's really close to 2. Now, what would happen if I added another 9 here? What do you think would happen? Any ideas?
To be even closer.
I would get another 9 here. What if I added another 9? I get another 9, another 9, another 9. And so we say that as x approaches 1, what is f of x approaching? F of x is approaching 2. So we say that the limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. We cannot have the value of the function at 2, but we can certainly say that it approaches 2. And that's the idea. So we kind of like gloss over that hole that is there. Okay, let's look at another one here. Okay, number 2. Let's find the limit. Okay, find the limit of f of x equals 2x plus 2 when x approaches 2. Okay, well this we don't have any problem with. There are no really bad values. So so 2x plus 2 is just a line, and x is in the domain. So we can just plug in 2 here. Okay, is 6. And so that is the limit. Now, why is that the limit? Why is the value at the limit? Because there's no bad values here. If we look at this graph here, right, 2x plus 2, it's going to look like this. And when x is 2, okay, that value, the value that we're approaching is the value. Okay, there's no bad value there. So it's okay to say, hey, the limit here as x approaches 2, okay, of 2x plus 2 is 6. We can just plug directly in. Now we couldn't do that before because when we plug directly in, we got a really bad value. But in this case, it works. Okay. Now what about a piecewise function? Okay, find the limit as x goes to 1 of g of x, where g of x is equal to 5 when x equals 1, and x plus 1 when x is not equal to 1. Okay. So we have a point 1, 5 when x is 1, but then we have the rest of the function, which is x plus 1, that's the equation of a line, when x is not equal to 1. Okay, so this, if I looked at the domain here, for this one, I'd say this is negative infinity to 1, unioned with 1 to infinity. Okay, and the 1 is not included in this line, but the 1 is included in this point. Okay, and so you would think that, you know, if it was just a straight line, then it would be 2, then, right, then you would think, well, g of 1 is equal to 1 plus 1, which is 2, but that's not true. G of 1, we're saying, is not equal to 2. G of 1 is equal to 5 here. So there's a hole in our line. Okay, and so what this looks like, again, is this. It looks like we have this line here, okay, line up like so. Okay, and then at 1, at 1, okay, 1, 2, we have a really bad point, okay, that doesn't exist here, but at 5, the point does exist, okay, so this is the point 1, 5, which does exist, but there is a hole in our line. So we're going to say, well, what's the limit of this value? Well, the limit isn't the 5. The limit is what are the values around the bad value? And what are they going toward? Right? What's the limit, okay, as x approaches 1 of g of x, okay, this is a piecewise function, g of x. Well, as we approach the limit from the left, g of x is approaching 2. And from the right, g of x is approaching 2. And so we say that the limit as x approaches 1, oh, I can't write. The limit as x approaches 1 of g of x is equal to 2. Okay, so the limit is 2, whereas we had this bad value. Okay, and we could see that by plugging in numbers close to 1. Again, if I wanted to plug in for, say, 0.999 or 1.001, we could use values that are close to 1, but they are not 1, and we would see that, oh yeah, g of x here would be 1.999, g of x here would be 2.001, and so we're getting numbers that are really close to 2, but they're just not 2. Okay, they approach 2. They approach 2. Okay, and since they're approaching 2 from both sides, okay, since they're approaching 2 from both sides, then the limit is 2. It has to be approaching it from both sides. Okay, let's try the next example here. Okay, example number 4. Okay, find the limit. Find the limit as x approaches 1 of h of x, where, okay, h of x is equal to, what is it equal to? It's equal to 2x plus 2 for x less than 1, and it's 2x minus 4 for x is greater than or equal to 1. So what's this going to look like? Well, we've got 2 lines, the equation of 2 lines here. This is a 4, by the way. That's a 2x. Okay. So we have 2 lines. They are parallel lines because of the 2 in front of the x. They just have different y-intercept. So we've got parallel lines, right? One has a y-intercept of 2. One has a y-intercept of -4. Just got rid of my ruler, but I'm going to bring this back, the ruler back. Okay, so I'm going to go 1 and 1 here, and 2. Okay, so I'm going to go like so. Okay, we'll do a 49-degree angle. Boom, that's one line. And this guy over here, we'll do a 49-degree angle. And we can see that those lines are parallel, right? Okay. But they're in pieces, okay? They're in pieces. Now, how are they in pieces? Well, this guy goes on forever that way. But there's a problem at 1. At 1, we jump lines, okay? So this guy here is 2x plus 2, okay? This guy here is 2x minus 4. And what happens at 1, okay, at 1, we end up jumping lines. Okay, so what is 1 here? 2 times 1 plus 1, that's 4, right? Okay, so this would be 1, 2, this would be at 4. Okay, and what I'm going to get here is an open circle. Okay. So again, let me create an open circle. Why open circle? Because I can't get to 1. Okay, I have to always be less than 1 on this line. This line is always less than 1. Okay. Always less than 1. Okay, so as I approach 1, okay, as I approach 1 from the left, I can't get there, but then I jump, and I am here, okay, when x is 1. So what's 2 times 1 minus 4? 2 times 2. So this guy down here is going to be at -2. Okay, the rest of this doesn't exist. Okay. Okay, and so we get this guy here. Okay, and so we want to find out a couple of things here. Okay, what is the limit as x approaches 1 of h of x? What's the limit as x approaches 1 of h of x? Well, as I approach this thing from the right, or sorry, from the left, let's do from the left first. As I approach x from the left, from the negative direction, okay, of h of x, where is this approaching? What value? Well, it's approaching 4 here, right?
4.
Okay, so that equals 4. Okay, what happens if I approach it from the other direction? Limit.
To -2.
Yeah, -2. Thank you, Giselle. X goes to 1 from the right of h of x. This becomes -2, right? Notice that these two numbers are not the same. Not the same. What does that mean, that they're not the same? Well, it means that since they're not the same, then the limit does not exist. So we would say that the limit as x approaches 1 of h of x does not exist. Okay, the limit itself does not exist. Okay, let's try another one. So number 5 here. Okay. So find A, the limit as x approaches 2 of 1 over x minus 2, and B, the limit as x approaches infinity of 1 over x minus 2. Well, that's interesting. Nice. Okay, so let's look at the graph of this thing real quick. Okay, let's look at the graph of this thing. So what does f of x equal 1 over x minus 2 look like? Well, it looks like this. Okay. I'm going to have what's called an asymptote at 2, okay, at x equals 2. Why? Because I can't have x equals 2. X cannot equal 2 here, right? X cannot equal 2. And so I get what's called an asymptote here for this. And the graph is going to look like this. Or the graph points on this graph, it's going to look like that. And then it's going to look like this. Okay, so it looks like that. So as I approach 2 from the left, I'm going to negative infinity. As I approach 2 from the right, I'm going to positive infinity. And negative infinity and positive infinity, they don't meet. They don't match. Okay, so the limit here does not exist. Okay, so the limit as x approaches 2 from the left, as I walk along this curve and I approach it from the left, I'm going to negative infinity. So that's 1 over x minus 2 equals negative infinity. The limit as x approaches, this is part A, by the way. Okay, limit as x approaches 2 from the right of 1 over x minus 2. As I approach it from the right, so I walk along the curve from the right. Okay, this is equal to positive infinity. These two are not the same, not equal. And so the limit does not exist. DNE, okay? DNE means does not exist. Okay, what about part B? What's the limit as x approaches infinity of 1 over x minus 2? Well, as x gets bigger, what happens to 1 over x minus 2? Doesn't that get smaller?
It approaches 0.
Yeah, exactly. As x approaches billion, this becomes 1 billionth, right? It's like it has an inverse relationship. As x gets bigger, 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 x minus 2 gets smaller, 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 and we can see that according to the graph here, it's approaching, okay? It keeps approaching and getting closer and closer and closer to 0. So we say that this does have a limit at infinity, and that the limit as x approaches infinity, because we can only approach infinity from the left, right? We can't get on the other side of infinity. Okay, we can only approach it from the left. So if you really want to think of this as a minus sign, you can, but it's implied that we're only approaching this from the left. Okay, of 1 over x minus 2, that equals 0. So the limit there is 0. Here it does not exist, and there the limit is 0. Keep it going, keep it going. Okay, exciting stuff, exciting times. These are good, these are Izzy's. I get them at Chipotle. They're sparkling blackberry. I treated myself to Chipotle today because I'm going through a breakup. It's really bad. It's a really bad breakup too. I've decided to break up with my teenage daughter. Yeah.
Okay, there's plenty to see.
That again?
Plenty of fish in the sea.
It's hard to hear you. Sorry, Alex. There are good breakups and there are bad breakups. And I was hoping this would be a good breakup, but it's not. It's turning out to be a bad breakup. So they say grandchildren are the reward for not killing your teenagers. I'm hoping to have some grandchildren someday. But plenty of fish in the sea. No, this is my daughter I'm breaking up from. So I'm breaking up with her. I'm done with her and her teenage attitude. I've had it. So again, it feels to me like a breakup, but More snark. Yeah, that would be true, but the problem is I don't really want to counter her bad behavior with more bad behavior. So that's the hard part. Like, it's hard because I was a really good kid, according to adults, right? According to adults, you're like, oh, I was a really good kid, and it's hard to see someone you love make really bad choices. So at this point, I just have to kind of distance myself from it. Otherwise, it's just going to make me go insane. Anyway, thank you for letting me share. My name is Jason. I'll be here all week. So, okay. Anyway, back to the stuff. Okay, back to the exciting world of limits, right? Yeah, I guess. Exactly. No, she's a normal kid though. That's the thing. I according to everybody else, I was abnormal. I was an abnormal kid. Like, I didn't really go through that whole teenage angst phase. Maybe I just saved it all up for my adulthood. So, who knows? Who knows? Anyway. So, okay, number 6 here. Okay, find, okay, the limit as x approaches infinity of 1 over x minus 2 plus 3. We want to do this numerically. It says find this numerically. Okay, we did it graphically. If we did it graphically, we would know that this is going to approach 3, right? Okay, this goes to 3 if we look at it, but we want to prove this numerically. So how would I prove this numerically that this thing is going to go to 3? Well, I'm going to plug in x and then f of x. Right? X and f of x. So 10. Right? So what would, if I plug in 10, this becomes 1 over 10 minus 2 plus 3. Okay, 1 over 10 minus 2. This is 1/8 plus 3. So this is 3 and 1/8, which is about 3.125. Okay. If I do 100, this is 1 over 98 plus 3, which comes out to be 3.0102. If I go to 1,000, this is 1 over 998 plus 3, which is 3.0010. Okay, is that infinity? Which one? Yes, this is infinity. Okay, or it's an 8 that somebody kicked. Okay.
Professor, did you assume it was going to be 3 because it's the y-intercept?
It's not the y-intercept. It's a asymptote is what it is.
Oh, okay.
It's an asymptote. Okay.
Oh.
Don't make that mistake, or you'll make an asymptote out of yourself.
Okay.
Thank you for the courtesy laugh. I appreciate that.
It was funny.
Okay. So as we go to infinity here, what do we see happening? This thing is approaching 3, right? So as we go to get bigger and bigger, it's 3, right? So again, if we were to graph this thing, what would this thing look like graphically? There would be an asymptote at 2 in the x direction. There would be an asymptote at 3 in the y direction, and it would look like this if you were to graph it. Okay, which you can do on a graphing calculator, or maybe we'll go to Desmos and I'll show you what this thing is doing on Desmos. Okay. So the limit. Okay, we get 1 over. I'm going to plug in y here if I can find that thing here. Okay. Okay, so y, y equals 1 over x minus 2, x minus 2. Okay, I don't care about your editing tips. Why do you keep coming up there? I don't want your editing tips. You keep your editing tips to yourself. Okay, I'm going to arrow over. Go away, Mr. Editing Tips. I'm trying to find out how to get rid of that thing. Okay, and then plus 3. Plus 3. Ooh, ooh, plus 3. Not times 3. Plus 3. Oh, you're so annoying. Okay, plus 3. And then what I'm going to do here, just to show what editing tips. I don't care about your damn editing tips. Go away. I'll get you to go away. Go away. Okay, go away. There, go away. Do the unhappy emoji. Okay, now go away. Be gone with you and your bad self. Okay. Okay, so let's do y equals 3. Okay, and you can see that this is the asymptote that I'm talking about. We could also do x equals 2 if we want to. X equals 2. Boom, that's the other asymptote. Let's go over here and let's look at this, right? So at y equals 3, okay, this thing is my graph. And what happens as I get bigger and bigger and bigger and bigger, I approach 3, right? If I zoom way out, you can see this thing, okay, I'm on this line, this graph here, okay, and I just keep going up, 56, 100, okay, and where are we at? Right, so we start approaching that 3 closer and closer and closer and closer to 3 as we go along. Okay, and so that is, it approaches the asymptote. Okay. Christopher is giving me the angry eyes. Why are you giving me the angry eyes? I don't understand. I don't speak emoji. It's like you're trying to speak to me. I know it. So maybe that's the problem. Maybe that's the problem is I don't speak emoji, and therefore I cannot relate to the younger generation. So it was for the puns. Oh, okay. I see. So emoticons. I could do a little winky face for you. That's about it. There you go. You people have too much time on your hands. That's all I have to say. Okay. It's all about growing up, growing older, growing bigger. I don't know. Who knows? Okay, let's get back to work. Back to work. I can't do it. Watch. There we go. That was it. Okay. I don't know. We're back to doing the emoticons, aren't we? That's little panda bear right there. Thank you, Darlene. Okay. So I have one. I do have one. Okay. So let me see if I can do this. Okay. So I'm gonna type a message here. Okay. So let's see if I can do this. Let's see. Boom. Let's see. Hello. Why is my oh, that's the wrong one. Let me get the right keyboard. So let's do this. Okay, that. And then what do we got? We got some of these. Nope, we don't. Okay, we got one of those. We got one of those. Okay, something like this. Just do a little something, little some. Okay, little like that. Okay. Oh, I gotta look it up. I'm screwing it up already. Okay, screwing it up. Screwing it up. That's okay. That's okay. That's okay. Where's the 8? Where's the 8? Nope, don't want that. Don't want that. Oh, yeah, I got it. Yes, I got it. I got it. I'm good. Boom. There you go. Nice. See, I do speak the emoticon there. Okay. So, boom. Okay. There is another thing that I missed on that, but it's there's the one with the if you do that one and you put a little tilde thing, it looks like Homer Simpson. Like, but I screwed it all up. So just Google Homer Simpson emoticon, and it comes up as that guy. It's close. Okay, close. Okay, anyway, let's go back. Okay, what about negative infinity? What is this thing gonna approach if I go to negative infinity? Right? What does this thing approach? Well, let's look at the limit. Okay, so the limit of this thing, the limit as x approaches 2, or no, x approaches positive infinity, okay, is going to equal 1 over x minus 2 plus 3 is equal to 3. That's the limit of that thing. Okay, what about the limit as x approaches negative infinity? Well, that just means I'm going to get a really small negative number and add that to 3. So a really small negative number added to 3, it's still going to approach 3, just going to approach it from the bottom. If I look at my graph here, as I approach infinity, okay, let me zoom in, do a little zoom here, zoom action. Okay, and so as we approach negative infinity, right, it's still going to approach 3, but it's going to approach it from the bottom. We're going to get smaller numbers, okay, then smaller than 3. These are all going to be negative values added to 3. But as I go to negative infinity, the amount that I'm adding becomes less and less, right? So again, if we do this numerically, x and f of x, we would say that this is 10, right? So this would be, well, sorry, negative 10. So this would be 1 over negative 12 plus 3, right? So that would be 2 and 11 twelfths, right? 2 and 11 twelfths. Okay. And then if we did negative 100, this would be 1 over negative 102, right? Which is going to be plus 3, which is going to be 2 and 101 over 102, right? Okay. How are we doing? Enough with the emoticons. Pay attention, please, people. Let's get back on track. That's cracking the whip there. Crack that whip. Okay. It's the nature of online education. You're just like, I got this chat bar in front of me, and this guy's talking about some really boring limit stuff. So I'm just gonna digress. I got my Izzy's. Boom. Boom. Okay. So number 7. Okay. Oh, sorry. This thing is going to go to, as the limit x approaches negative infinity. What's this thing approaching? Wasn't it still approaching 3? It's just approaching it from the bottom. Okay. It's approaching it from 2. We're going up 2 and 11 twelfths, 2 and 101 over 102. This thing. x minus 2 plus 3 is still going to be 3. So regardless of which direction I'm approaching infinity from, I'm still approaching 3, which makes sense because that's the asymptote. 3 is the asymptote. And whether or not I'm approaching from positive infinity, I'm approaching 3, y equals 3. Or if I'm approaching from negative infinity, I'm still approaching 3, y equals 3. Doesn't matter. Doesn't matter which direction I'm approaching this from, whether it's positive infinity or negative infinity, I'm still approaching 3 from top of bottom. Okay? Okay. Let's do some algebra. Let's spice it up and let's do some algebra with these limits. Okay, so 1.2, algebraic limits, okay, and continuity. Okay, continuity. Okay, algebraic limits and continuity. Okay. Okay, limit properties. Let's look at our limit properties. Limit properties. There we go. Limit properties. Okay. So 1, the limit as x approaches a of a constant is equal to a constant. Okay. Makes sense because it's not going to be dependent on what a is. Okay. It's a constant. It's always a constant. If we look at a constant function, what's a constant function? It's a horizontal line. That constant function, y equals c, is always going to be constant regardless of where I am. It's always going to be the same value, regardless of what x is. Okay, this is a constant, by the way, constant. Like 3. The limit of 3 is 3. Imagine that. Should kind of go without saying. Okay, what's this limit? The limit as x approaches a of x equals what? Any guesses? Limit as x approaches a of x. We have a guess of x. What does y equals x look like? Wasn't that just this line here? Isn't the y value and the x value the same? So as x approaches a, what's y approaching?
A.
Are you Canadian, Paul?
Me?
Yeah.
No.
No, you're always saying A. Like CA, NA, DA. Just wondering if you're from Canada. Okay, so A. So the limit as x approaches A. I'm just joshing with you. Okay, so don't take what I say personally. Okay, I dad jokes for days. Exactly. Okay, they're uncle jokes. I guess they're dad jokes because I'm a dad. So I guess they're. But in Teen Titans they call them uncle jokes. Teen Titans. Okay, booyah, booyah. Okay, so. Number 3, okay, Robin tells all these uncle jokes. It's where I get all my material from. I get it from Robin, Teen Titans. Check it out. Okay, limit as x approaches a of x to the m is equal to a to the m. Okay, a to the m. Okay, number 4, the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. Okay, there you go. Okay. So number 5. Okay. Okay, number 5. Okay, so limit. I'm sorry. I'm cracking up today. It's COVID. COVID is getting to me. Is anybody else? COVID is getting to them. I ran out of my ism. COVID sucks. All I can
Does.
say. COVID sucks. I'm over this. Exactly. I'm over COVID. COVID sucks. So we'll just say that. COVID sucks. Okay, sorry. Back on track. Okay. You know the hard thing about COVID is the people that I want to see, I can't see. And the people that I really don't get along with, I'm stuck with. That's the problem. like I love you and all, but seeing you 24/7 is a little much after 6 months. Go do something else. I need a break. I need a break. Right. Break. Okay. I lost my smell and taste from COVID. You had the COVID and you got over it? Oh my gosh. You had the COVID. Wow. I'm so sorry. Hide the keys. Okay, let's move on. So number 5, the limit as x approaches a of c, a constant times f of x, constant times f of x is equal to c times the limit as x approaches a of f of x, right? So all this is saying is that if I have a constant times a function and I take the limit, all I can do, I can pull that constant out. The limit of a constant times a function is the constant times the limit of the function. Okay, so basically it looks like this. We take an example here. The limit as x approaches 2 of 2 times x plus 2 is equal to 2 times the limit as x approaches 2 of x plus 2. Now, is this true? Well, if I were to distribute this, this would become the limit as x approaches 2 of 2x plus 4 equals 2 times the limit as x approaches 2 of x plus 2. Does this make sense? Well, what's the limit of x approaches 2? Well, that's 2 times 2 plus 4, which is 8. This is 8, okay? Because as I approach this thing from the right, it's 8. As I approach this thing from the left, it's 8, so it's 8. What about over here? Well, this thing is 2 plus 2, which is 4. So the limit of this thing is 4, but then multiplied by 2, and 8 is equal to 8. So it says check, it checks out. Okay, number 6. Okay, the limit as x approaches a, okay, of f of x times g of x is equal to the limit as x approaches a of f of x times, you probably guessed it, the limit as x approaches a of g of x. So the limit of a product is the product of the limits. Okay, I kind of like saying that. That has a nice ring to it. Okay, the limit of the products is the product of the limits. Okay, the limit of the products is the product of the limits. Things that make you go, Okay, the limit of the products is the product of the limits. Limit of the product is the product of limits. Just rolls off the tongue nicely. Okay, so let's do an example here. Okay, example 1. Let me change colors so we know it's a new example. Okay, let's find the limit. Find the limit as x approaches 4 of x squared minus 3x plus 7. Okay, so I'm going to break this up. I'm going to say this is the limit as x approaches 4 of x squared plus the limit as x approaches 4 of negative 3x plus the limit as x approaches 4 of 7. Okay. Okay, so what is the limit as x approaches 4 of x squared? Well, we saw that that was rule number 3. Okay, so from rule number 3, we know that the limit as x approaches x to the mth power, okay, is really a to the mth power. So this is just going to be 4 squared. Okay, what about this one here? The limit negative 3x, that's just the constant times the limit. Okay, that's number 5. Okay, so number 5 here is rule number 5. Tells me that I can just plug in negative 4 here. It's negative 3, okay, times the limit of x is just, okay, this is actually, it's 4, it's number 5 and it's number 2. Number 5 and number 2. Okay, how is it number 5 and number 2? Well, I could do this. I could pull the negative 3 out in front and go the limit as x approaches 4 of x, right? The limit as x approaches 4 of x, okay, is, well, what is that? That's just 4, right? Which goes back to number 2, right? Rule number 2. And then what's this, since this thing is 4, what's negative 3 times 4? That's negative 12 plus 4 squared plus, okay, the limit as x approaches 4 of 7. Well, what's the limit of a constant? It's just the constant, right? It's just the constant. So okay, so this is just plus 7. Okay. Okay, there is a reason we're going over this, by the way. You're just like, why the hell am I learning this stuff? Okay, there is a reason. There is a method to the madness, and we will get to applications that you cannot do without this stuff. Okay, but again, you got to walk before you can run. And we're just learning to walk right now. We're embracing this idea of a limit. What is a limiting value? It's the value that we approach. It's the value that we can approach even if we have bad things happening. Okay, we have these little monsters called discontinuities in our we have something called break discontinuities. We have jump. This is a jump discontinuity. Okay, this is a jump. Mac Daddy will make you jump. Crisscross will make you jump. That's from a long time ago. Okay, so this is a jump discontinuity. Why is it a jump discontinuity? Because it jumps. Okay, it jumps. We've got these bad things happening. This thing is called a removable discontinuity because I can remove the discontinuity by just filling it in. Okay, this is a removable discontinuity. Movable. Why? Because I can just take this bad point out and throw it away. It's called a removable discontinuity. This is a jump discontinuity. This is a removable discontinuity. Okay, there are other discontinuities. Okay, like when we have asymptote, we have this. And we go here, we have other discontinuities. And it's like, well, what do we do with our functions that have really bad things that happen to them? We use limits to get around these bad functions, these bad places in the functions. Not all of the function is bad, right? Everything in this function is good is workable up to this point. And then everything after that is good and workable. It's just this one bad point that I don't like. I want to get rid of it. So just get rid of it, fill it in, boom, remove it. Okay, and how do we remove the discontinuity? We talk about the limit of the function. And instead of talking about the value at the function, we talk about the limit. We talk about the limit at that function at that value. And so if we can talk about the limit at that value, then we can actually have something to talk about. Otherwise, we have nothing to talk about because there's nothing there. It's a big black hole. Okay. So that's kind of the main idea. You know, again, we have to kind of walk before we can run with this thing. So what is this? This is 16 plus negative 12 plus 7. This is 4 plus 7, which is 11. So the limit to this function, right? The limit to this function here was 11. Boom, find the limit. It's 11. Okay. Let's do some more with the algebras. Okay. For any rational function, okay, theorem. Everybody know what a theorem is? It's just a provable statement. A provable mathematical statement is a theorem. Just something that you can prove. It's a theorem. Okay, it's not a theory, that's unprovable. Okay, it's a theorem, which is always provable. Okay, so let's talk about the theorem here, which is a provable statement, which is for any rational function f of x, the limit as x approaches a of f of x is equal to f of a. Is equal to f of a. Okay, all that's saying is, look, all we have to do is plug in a every time we see x and evaluate, and we're good. Oh, well, that's easy. Okay. So let's do some of these. Boom. Okay, what's the limit as x approaches 2 of x to the 4th minus 5x cubed plus x squared minus 7? Now we don't have to go through that whole, like, using all these rules. Now we can just substitute directly in every time we see an x. And say, oh, okay, the limit of this thing, if it's a rational function, okay, if it's a rational function, if it's a polynomial especially, we just plug directly in. And say this is 2 to the 4th minus 5 times 2 to the 3rd plus 2 to the 2nd minus 7. That's what the limit's going to be. Okay. And so we just evaluate this. 2 to the 4th is 16 minus 5 times 8 is 40 plus 4 minus 7. This is 20. These two are 20. 20 minus 40 is negative 20. Minus 7 is negative 27. So this is negative 27. Oh, that's the limit of that value. We just plug directly in. That's easy. That's algebra. That's easy algebra stuff. Okay, what about this one? Number 3 here. Okay, the limit as x approaches 0, the limit as x approaches 0 of the square root of x squared minus 3x plus 2. What's that going to be equal to? We'll just plug in 0. Well, that's just going to end up being the square root of 2. Because 0 minus 0 is 0, plus 2 is 2. That's the square root of 2. Oh, okay, cool. Easy. Easy peasy. What does that mean? Okay, the limit as x approaches negative 3 of x squared minus x minus 12 over x plus 3. Well, here we actually do have to find the limit. Right? We have to find the limit because x cannot equal -3. So we can't just plug in directly into this because we would get division by 0. So what can we do? Well, we can simplify this. We can factor and then simplify. Oh. So this we're going to factor. We're going to factor this. Two numbers that multiply to -12. Multiply to -12. Multiply to -12, but add to -1. Okay, so we want them to add to -1 and multiply to -12. Okay. Well, how about -4
3.
and 3? Yes. Is that Alex?
Mario.
Mario. Thank you, Mario. Okay. So yeah, so -4 and 3. Okay, so that's going to tell me that I'm going to factor this guy into x minus 4 times x minus 3, or sorry, plus 3, all over x plus 3. And lo and behold, what cancels out? The x plus 3. Gets rid of that one bad value. We call that removing the discontinuity. What do we do? We removed the discontinuity, the bad point. Okay, where it was discontinuous, we removed it. Boom, removed. Goodbye. Goodbye. Okay, and we get the limit as x approaches -3 of this thing here. Well, what are we going to do now? Well, we're just going to plug in the -3, which becomes -7. So we know the limit was -7. Okay, one last one that we want to cover is what happens when we have more than one variable. The limit as h approaches 0 of 3x squared plus 3xh plus h squared all over, oops, not all over, it's just that, just this. Okay, so what are we going to do? Well, we're just going to plug in where h is equal to 0. And so what's the only thing that survives? The only thing that survives? H goes 0 here, h goes 0 there. The only thing that survives is the first one, right? So that's 3x squared. So the limit of that is 3x squared. Okay, even though there was an x there, we don't care about the x. We just care about where is the h going. The h is going to 0. The x can vary. We can let the x be anything we want it to be. Okay. Okay, let's talk about continuity. Okay, continuity. Okay, continuity. I miss my college. I think that's the problem today. Is I'm mourning my college. I'm mourning the people and the smiling faces and everybody being happy. I miss Subway. I miss Subway. So I don't care about you guys. I care about Subway. That's what
I miss Taco Bell
I miss.
when it used to be there.
Yo, used to be a Taco. You've been there for a while, huh?
Yeah.
Eish.
It was just a
Gotta
lot
move on.
quicker than Subway, you know? Because Subway, there's always a long line, so it's hard to,
Gotta move on, man.
yeah.
The In-N-Out across the street. Yeah, I miss that too.
Oh, that for sure.
Even the CVS where they got those little, what do you call them? Drumsticks, right? The little, are they called drumsticks? I think they're called drumsticks. They're ice cream, right? Ice creams. Just walk over to CVS, grab a nice little ice cream cone. There. No. Yeah, I kind of miss it. Oh, I'm gonna be missing it too, because they just informed me that I will be teaching from home until next summer. So, yeah, sucks. That's okay. It's all good. It's actually not all good, but at least I still have you guys.
Wait, really? Till next summer?
Yeah. No, not everyone is home till next summer. The math people are home till next summer. I just happen to be one of the lucky ones that teaches math. And yeah, we're more than likely 99% certain that I will be teaching from home in the spring. So yeah. Now, if you know, they're going to open up the campus in stages. And guess who gets to be last? Yep, that's it, math and English. Woohoo. We get to be last. So, whatever. Yeah, so take a chemistry class, that's all I can say. So, take a culinary arts class. You'll be first on campus. Anyway, okay, continuity. Okay, continuity. Okay, what does it mean for a function to be continuous? Well, a function, okay, f is continuous at x equals a if the following three criteria are true. If all of these are true, then it's continuous. Okay, 1. Okay, f of a exists. 2, the limit as x approaches a of f of x exists. And 3, the value and the limit are equal. Okay, the value and the limit are equal. The value and the limit are equal. Okay, so what does this mean? What does this mean graphically? Okay, this is what this means. It means that let's look at x equals a. Let's look at x equals a here, right? And we have some sort of function. I'm just gonna do a generic function here. Here's a function, okay? There's my mother function. Oh, sorry, I didn't mean to curse. Sorry. Okay, this is my function here. Okay, so let's keep it PG. Let's keep PG. Okay. So here is my function, and how do I know that it's continuous at a? That there's no breaks or jumps or weird things happening at a? Well, I know it's continuous at a. It's continuous. Okay, it continues at a. We're just interested in what's happening at a. Okay, if 3 things occur. The first is the value, does the value at a exist? Is there a value for a? Okay, it could be here, it could be here, it could be here, but we just need there to be a value that exists at a. Does it exist? Sure. Could it be anywhere? Sure. Doesn't have to be here, doesn't have to be here. It could be down here, for all I know, but it needs to exist. Okay, so criteria number 1, does it exist? Check. Does the limit exist? Okay, does the limit exist? Well, as I approach from the right, sorry, from the left, okay, from the left, okay, from the left, okay, and then from the right, okay, from the right, crisscross. That's the cha-cha slide, sorry. Okay, crisscross, y'all. Okay, so from there and then from there, yes, does the limit exist? Yes, the limit exists. Now, how do I know it's continuous? Well, this thing that I've drawn here, this thing that I have drawn here, okay, no drums. Okay, this thing that I have drawn is not continuous. Why? Why is this not continuous? Because the value at A is not the same as the limit. Notice that the limit and the value are two different things. So this does not work. It is not continuous. Oh, okay. How would I make it continuous? How would I make this a continuous function at A? Well, I would fill the hole. Now is it continuous?
Yes.
Yeah, now it's continuous. Now it's continuous. Why? Because f of A existed, and the limit existed, and f of A and the limit are the same value. Boom. And so now I know that, oh, I can get from the right side to the left side without any breaks or gaps or jumps. And if we say that a function is continuous, a function is continuous for all x, then we would say that every single point on this function has no breaks or gaps or jumps. The informal definition of continuity, informal definition of continuity is that if you can not lift your pen from the paper while drawing the function, it is continuous. Okay? If you have to lift your pen from the paper, then it's discontinuous. That's the informal definition. We want no gaps, no cuts, no butts, no coconuts. No, I'm just kidding. Okay, no gaps, no jumps, or holes. Okay, or we'll say no holes. No holes in the graph. Okay, in order for it to be continuous. No gaps, no nothing. Okay, so let's see what we got here. Is, okay, the function f of x equal to x squared minus 5. Is that continuous at x equals 3? Is it continuous at x equals 3? Okay, is this thing continuous at x equals 3? No. 1. What is f of 3? Does that exist? Well, of course it does. Just plug it in. That's 3 squared minus 5, which is 4. Okay, that exists. Number 2, what's the limit as x approaches 3 of x squared minus 5? Well, what's the limit of this thing? Well, if we were to look at the graph here, okay, and we were to say, oh, what's happening at 3, right? We would get a graph that looks like this. This is 1, 2, 3, 4, 5, and it would look like this. Okay, it's a parabola that's opening up, and at 3, 1, 2, 3, we are at x equals 4. Okay, 3, 4. So this is equal to 4. And is the third criteria met, or is criteria 1 equal to criteria 2? Yes. Okay, is criteria 1 equal to criteria? Yeah. So we can say that f of 3 does equal the limit as x approaches 3 of x squared minus 5. That checks as well. These two are the same, therefore it is continuous at 3. Okay, it just happens to be continuous everywhere. Not necessarily the case for everything, right? Okay, not necessarily the case for everything. Okay, for example, let's do an example 7 here. Okay, is f of x equal 1 over x minus 2 continuous at x equals 1? Is it continuous at x equals 1? Well, let's think about this for a second. Let's go through our criteria. Our first criteria is, does f of 1 exist? 1 over 1 minus 2 is 1 over negative 1, which is negative 1. That works. Number 2, what's the limit? What's the limit as x approaches 1 of 1 over x minus 2? Right? We could do this numerically. We could plug in numbers that are really, really close to 1. We got value here, so it should just be the same thing. It should be 1 over negative 1, which is negative 1. So that checks. So is it continuous at 1? Yes. Okay, yes. You know, criteria 1 is the same as criteria 2. We could say that f of 1 is equal to the limit as x approaches 1 of 1 over x minus 2. That's correct. Therefore, is it continuous at 1? Yes, it is. Why? Because it looks like this. It looks like this. It says, hey, this is negative 1 when x is equal to 1. This is my asymptote, x equals 2. And then at 1, negative 1, we've got a point, and it looks like this, right? Okay. And so the point and the limits are the same. Okay. Okay. So that's kind of a messy graph there. Okay. So the value at 1, negative 1 is the limit, and the limit is the value, therefore this is continuous at that value. However, we'll call this 7a. 7b, for 7b, is the function f of x equal 1 over x minus 2. Is this function continuous, okay, is that continuous at x equals 2? Now we're changing the game by saying, well, what happens at x equals 2? Is this still continuous? Well, what's the first criteria? The first criteria is that it has to be defined at 2. Well, it's defined at 2. Let's plug it in. F of 2 is equal to 1 over 2 minus 2, which is 1 over 0, which is undefined. So this one first fails. That fails. Boom. Done. No, not continuous. Not continuous. Why? Because the first criteria fails. Not continuous. Not continuous. Okay, let's do a last example here. Last example. Okay, number 8. Number 8 is, oops, let's move this over. Okay. Okay, number 8 is function g of x given by g of x equals negative x plus 3, x squared minus 3 for x less than or equal to 2, and this is for x greater than 2. Okay, so we've got a couple of different functions going on. Is this continuous? Is the function given by this continuous at x equals 2? Okay, is this continuous at x equals 2? Okay, well, this is a piecewise function, but I want to see, are there any gaps in or breaks in my graph here? Okay, well, let's see what happens. Okay, maybe instead of graphing this by hand, I'm gonna cheat. I'm gonna go to Desmos and graph it. Okay, so if I do Desmos here, and I graph this guy, let's graph the first one. Let's graph y equals, okay, y equals, okay, negative x plus 3, negative x plus 3. Okay, so that's that line. Okay. Can I put a domain in here? Let me see if I can put a domain in here for this guy. Let me see here. Escape. Okay.
Professor, can't you just plug it into the first function where x is equal to or greater than 2?
Say it again. There's two functions here, right? There's two functions.
Yes, the first one where x is greater than or equal to 2. So you would plug it into the negative x plus 3, and it'll give you 1, no?
Less than or equal to 2, right?
Yeah.
Yeah, let me just show you what's going on here, though.
Mhm.
With the graph. You're only looking at it from one side, unfortunately. Okay, because of the way that it's. Let me just put in the other one here real quick. So y is equal to, oops. Okay, y is equal to, okay, oops. Y is equal to x squared minus 3. Let's look at x squared minus 3.
It's a parabola.
X squared minus 3. Boom, okay. So now, let's see what's happening here, okay? See what's happening here. Now, one of these is only valid, okay, for, I wish I could edit this. Convert to a table, duplicate, no, I don't want to do that. Done. Okay, so I wish I could create piecewise function on here. There should be a way. Let me see if I can do this. Okay, real quick. So, okay, edit domain. Okay, to restrict the domain, I use braces. Nice. Okay, let's just use some braces here. Yes, that's good. Okay, so this is going to go from negative infinity, okay, from negative infinity to miscellaneous. Nope. Go back. There we go. Okay, so let's see if we can restrict the domain here. I'm going to go from, say, negative 1,000 to where's the, here we go. So this guy here, control. Nope, I gotta use the keyboard, I guess. Okay, let's use the keyboard. Okay, so that there, and I'm gonna say that I'm not gonna go from negative 1,000. I'm just gonna go, let's just say negative 10. Okay, negative 10. Okay, on this graph, comma, and then 2. Okay, 2. I want 2 to be, okay, it's only going to go from that and then do a brace. Okay, did that do what I wanted it to do? I don't think so. Do I need a comma here? No, the frick. It's not allowing me to do that. Also use the restrictions. Anyway, for whatever reason, it's not letting me do that. Oh, I see. Oh, no. Okay, I get it now. I get it now. I get what I did wrong. Okay, so this is got to be like so. It's got to be with this guy here. Oh, look at that. Ooh, nice. And this guy here. Boom. Nice. Okay. So, like so. Okay, let's see if we get rid of that. This guy. Nice. Look at that. I like it. I like it. I like it a lot. Okay, now what happens if I restrict it on this one? Okay, this one's going to be restricted from 2. We'll go all the way to 10. 2 to 10. Okay, 2. Okay, is less than or equal to. Okay, less than or equal to. Less than or equal to. Okay. Oh, this one should be actually the other way around, right? Less than or equal to 2. So let's do this guy here, less than or equal to 2. This one's going to be greater than, less than, because we want to be bigger than 2. So we're going to go like so. Backspace. Nope. I want the back of space. Backspace. I'm just going to use the keyboard on this one. Okay, backspace, and then this, boom, and then X, nope, little x, okay, X, and then less than or equal to 10. Let's go less than 10. Less than 10. Boom, look at that. Okay, now look at that. Is this thing continuous? According to the graph, would I have to pick up my pen at all? No. Why? Because as I reach this point here, this is 0.21, right? They both contain that point. Here it's 2 undefined, which is an open circle. You can see that it's an open circle there, right? So it's an open circle on the parabola. Okay, it's an open circle on the parabola, but on the line, it's a closed circle. Okay. Closed circle. Okay, so is it continuous? Yeah, let's prove that this is continuous. Boom, it's continuous. Does it look continuous? Yeah, it's continuous. Why? Because this guy, the red, fills in the hole for the blue. See how on the blue it's a hole, but on the red it's filled in. Okay. Okay. So it is continuous. Let's quickly. We went over that, Maria. Just watch the video. Okay. I have office hours on Thursdays as well, so keep that in mind. Okay, so 1. What's g of 2? G of 2, well, it would be negative 2 plus 3, which is 1. So 2 comma 1, does that exist? Yes. Okay, number 2, does the limit as x approaches 2, okay, what does that equal? Well, as we go from the right, okay, that's negative x plus 3, which, plug it in, that equals, okay, 1. Okay, from the left though, right, because we're on that line, right, from the left, we get this parabola, right? From the left, what's the limit though? What's the limit approaching? The limit is approaching 2. I'm sorry, it's approaching 1. As x approaches 2, the limit approaches 1. So the limit as x approaches 2 from the right of x squared minus 3 is still 1. That's the limit there, right? The limit. X approaches 2 from the right. So what is the limit as x approaches 2? X squared minus 3, that is equal to 1. Why? Because those two are the same. Now, is the limit plus the function value the same? Are these two the same? Yes. Therefore, criteria 3 is satisfied where g of 2 is equal to the limit as x approaches 2 of x squared minus 3. That is correct. Therefore, the function is continuous at x equals 2. Okay, one function filled in the holes of the other function. Okay. I believe, yes, I did cover it at the beginning of the class. It will be on YouTube in about a half hour. Okay, if you have any other questions that you want to go over, I'll stick around for another 10 minutes. Other than that, I will see you in office hours. No, yes, I'll wait on Thursday. No, office hours are, yeah, at 5 o'clock on Thursday. So I'll be in my office at 5 o'clock on Thursday if you have any questions about limits. Okay? See you guys later.
Professor, can I ask you about one of the I didn't get to write down one of the hold on, the limit properties, number 6. I didn't get to write that one down.